Hello from Chem Help ASAP. There are three key ideas that we will cover in every NMR spectrum: chemical shift, multiplicity, and integration. To help us with these three ideas, we have a proton spectrum of two fairly different molecules: 3-amino 1-propanol on the bottom and para-tolualdehyde on the top. Note that these are simulated spectra from NMRDB.org. NMRDB.org does not simulate hydrogens on nitrogen and oxygen, so those signals are missing. How do we talk about the differences in these spectra? We will focus on chemical shift, multiplicity, and integration. First, what is chemical shift? Chemical shift is the position of a peak or cluster of peaks on the x-axis. Chemical shift can be described qualitatively. Peaks on the left of the spectrum are called downfield, deshielded, or low field. Peaks on the right are called upfield, shielded, and high field. We can also directly refer to the numerical values on the x-axis. This is a quantitative description of chemical shift. The units on the x-axis numbers are in parts per million, or more often just called ppm. Most hydrogens in organic chemistry fall within a range to the left of the screen of 0 to 13 ppm. For our two molecules, notice that the ranges of the x-axes are not the same. The top spectrum runs from about 2 ppm to 10 ppm, and the bottom spectrum is more like maybe 1.5 ppm to 3.5 ppm. It's common for spectra to be cropped to remove regions that have no peaks. For our two molecules, the hydrogens are not the same. Some are close to an oxygen, some are attached to a benzene ring, some are close to a nitrogen. These differences determine the exact position, the exact chemical shift of the peaks in the spectra. Second, what is multiplicity? Multiplicity describes the shape of a signal from a specific hydrogen. Let's pick one type of hydrogen in 3-amino 1-propanol on the lower part of the screen. Let's look at the CH2 hydrogens in the middle of the molecule. The signal for those two hydrogens, which are identical by symmetry, show up here in the spectrum at a chemical shift of about 1.8 ppm. The shape of this signal is different from the signals at around 3.3 and about 2.6 ppm. The shape of the signals, the multiplicity of the signals, reveals useful information about the hydrogens that are next door to the hydrogens in question. Third, what is integration? Integration refers to the intensity of the signal of each hydrogen in the molecule. More precisely, integration is not just about the height of a peak, but about the area beneath a peak. So although these peaks are very narrow, we can go to the CH2 group we were just talking about and try to shade this region underneath the peak. The area below the signal, the integration of this signal, when compared to the integration of other signals, gives us a sense of how many hydrogens are causing each signal. This type of information is very useful for determining or confirming a molecule structure. So this has been a very quick introduction to the three ideas of chemical shift, multiplicity, and integration. Each idea needs further exploration, but at least we understand what each term means.